live. Okay, I think I'm live. Let's just check the audio stuff. Okay, just a sec. Just waiting for audio to start. Yeah, I think everything is working. Audio is okay, right? Can you just check? Hey, folks, just, hey, yeah, I think the audio is also okay. Hey, good evening, folks. Thanks for joining in on a Saturday evening. Just give me a sec. Okay, I think everything is good. So just give me a sec. Hey, good evening, folks. So yeah, so what we're planning to do today is there were a bunch of good questions asked by some of you in the comment section of videos and problems and stuff like that. So we have already we have answered most of these questions, but we thought we'll also cover these questions in the interest of everyone so that everybody can benefit from these answers. Some of them we thought it's better to do a video answer, and that's what we're doing in this live session. Okay. So okay, so let's go through each of these. Probably we should wait for 2 more minutes before we get going. So yeah, another thing. So somebody is asking, can we cover DSC operating systems, computer networks, DBMS before August? Ayush will try and cover as many as possible before August, but see, we have to. This is a big confusion or a big responsibility that we have on our shoulders. We have to take everybody together, right? Certainly, the next very topic that we'll do would be C programming. So we'll start the second batch also with C programming. Even for first batch, we'll do C programming right after this because many students have asked for it, especially those students who are preparing for placements and stuff like that. So we'll certainly do C programming, some discrete maths, because discrete maths is certainly something that has been requested. We'll try and accommodate as many requests as possible, and we'll try and order them. But I'll not be able to give you a concrete promise on this because things will be delayed slightly here and there. Like for example, this whole graph theory exercise, right? All the graph algorithms that we have. So it has taken more time than we expected for students to cover. I think only one person has finished everything by today morning. So we delayed pushing out content also today. We thought we'll do it from Monday, especially the greedy algorithms and dynamic programming and complexity classes. There are just 3 more topics left. I think we can finish those in like 3 to max 4 days, right? So so why don't we classify edges for BFS? Because this classification is not useful actually. So so Ayush, the question here is about campus placements. It depends on the company that is visiting. There is a huge spectrum of companies that come to campuses. Like for example, if you're talking about top-notch companies, they don't care as much about other subjects. They mostly look for programming, data structures, and algorithms, and they don't even look at gate-level questions. They mostly look at your ability to solve a problem and write functioning code in 20 minutes, right? Oh, Akash, yeah, we'll surely add more assignments for graphs. We will do that. So we are just waiting to finish rest of the contents in data structures algorithms. Then we'll give you much larger assignments, many more problems across the spectrum of all the topics in data structures algorithms. That will be like a subject revision. Till now, we have been doing topic revision and topic practice. Once we finish greedy algorithms, dynamic programming, and just a second, yeah. So when we finish greedy algorithms, dynamic programming, and complexity classes, we will certainly give you many more problems to solve. Okay, so don't worry about practice. We are too focused on practice. Anyway, let's dive in. Since I think many of you are already here, let's dive into some of the notes that I've written based on the questions that you have. Also, just in the interest of time, I thought it would be beneficial if you write notes so that I can cover these topics faster, right? So that we can also have some time to discuss miscellaneous stuff. So what's happening right now was if I actually write it down as I explain you, it's taking significantly longer period of time. So I've written all of the notes, and of course, anywhere you're stuck, I'm here to help you. Okay. So, okay, let me just screen share here and dive into it. By the way, I'm doing this. Okay. Where am I? Okay, share. Is there a problem? Okay, I think there is a problem with screen share here. Chrome wants to share the contents. Okay. Okay, I want to share. Okay, sounds good. Hide this. Okay, so yeah, I hope everybody can see the screen now. Just give it a second. I've just turned off my camera and changed the screen to a black screen. Okay, so we'll go step by step here. I hope the screen is visible. Okay, yeah. Uh, anyway, I have Subbarao here to help me with this. If there's any problem or anything, he'll surely intimate me and we'll sort it out together. Okay, so let's go step by step. Okay, so this is one of the very good questions that was asked, right? So if you notice, this question was actually there in recurrence relations, right? So when we solved recurrence relations, right, when you've seen recurrence relations, we came across this problem, and this question we couldn't solve it that day because we ran out of time. This is a slightly harder question, to be honest. This is actually a hard question, right? And for this question, we gave four options, and we said which of these options is true. So we had four options A, B, C, D. So let's solve each of them. This is a very time-taking problem also. This is a very time-taking problem, and this is actually a harder problem that some of you got stuck with. So we thought we'll anyway answer this also in this session, right? So this is the recurrence relation that is given to you. It says Tn equals to Tn by k plus T3n by 4 plus n if n is greater than equal to 2. Remember, there is a k here, and 1 if n equals to 1. So nothing is mentioned about k. Now, the first option that we have, and we have to say if each of these options is true or false. The first statement or option that we're given here is Tn equals to order of n power 3 by 2 when k equals to 3. Right? So when k equals to 3, what happens? This becomes Tn equals to Tn by 3 plus T3n by 4 plus n. Okay, and some of you have asked us to solve this using recurrence trees, right? Some of you have asked us to solve this using recurrence trees. So we thought we'll solve it to you. It's not very hard. It's doable. It's non-trivial, but doable. Okay. So let's assume I have a tree that starts with n nodes. The recurrence relation is Tn. The recurrence relation here is Tn is Tn by 3 plus T3n by 4 plus n, right? So this is the recurrence relation that I have. So given this recurrence relation that I have, so what happens now? Just give me a second. Let me get a pointer. Okay. Okay. So given this recurrence relation, what do I have? I have two options here: n by 3, 3n by 4. So these are the two ones that I'll get. And anyway, I have this n term here, right? I have this n term here. Now, when I break this n by 3, I'll get again this 1 by 3 is anyway there. So this become 1 by 9 into n and 1 by 3 into 3 by 4 into n. Because look at this, every n is divided into 1 by 3 into n and 3 by 4 into n. Similarly, 3 by 4 into n will be divided into 3 by 4 into 1 by 3 n, 3 by 4 into 3 by 4 n. Right? Now, if you sum up both of these, so to combine both of them, remember to combine both of these, we have n, right? That's what this recurrence relation says, right? Now, to combine both of them, we'll take n by 3. To combine both of them, we'll take 3n by 4. So if you simplify this, you get 13n by 12, right? So similarly, if you keep going on, at kth level, what you have is this. At kth level, so if you go through this left path, right? At kth level, you'll have 1 by 3 power k into n. This right path, if you notice this right path, right? We have seen similar examples like this, right? This right path will have 3 by 4 power k into n, right? And the sum of all of them, the time complex to combine all of these solutions will be 13 by 12 power k minus 1 into n. You can verify this. You can actually expand it to one more level. And actually, when you simplify it, you will get 13 by 12 power k minus 1 into n. Right? At kth level, this is what you will have. Right? And if you notice, this path is going to be shorter and this path is going to be longer. Right? Because you have 3 by 4 here. So if you have n here, this is 0.75 n. This is 0.33 n. Right? So what you have here is this path is longer. Right? So what is the length of this longer path? Right? So if you think about this longer path, this is going to be the longer path. Right? This path is going to be longer. What is the length of this longer path going to be? Let's assume the length of this longer path is k. Then k is going to be equal to log n base 4 by 3. Because you have 3 by 4 here. Remember, you have 3 by 4 here. The inverse of this will be the base of your logarithm. Right? This, we have seen other examples also in the previous problems, which are exactly like this. Now comes the fun part. Okay. Now, given this, look at all the terms that I need to add. Here I have n, then I have 13n by 12, then I'll have 13 square n by 12 square n, so on and so forth. 13 by 12 power k minus 1 into n. Now, when I sum up all of this, this is what I'll get. This is the total time complexity I get. Now I'll remove n from here. I'll get 1 plus 13 by 12 plus 13 square by 12 square, so on and so forth, 13 by 12 power k minus 1, right? So this is basically a geometric progression, right? With r. So this is the sum of the geometric progression, right? When r is when r is greater than 1, this is the sum of the arithmetic progression. And what is r? R is 13 by 12 and a is 1. So this is the formula for sum of not arithmetic progression, sum of GP, geometric progression, not AP. I'm sorry. Okay. So if you replace this, if you use this formula, so this sum will become n into 13 by 12 power k minus 1 by 1 by 12. Right. So this is what you'll get. Right. This is basically a simplification using this formula. If I just use this formula and if I simplify this, this is what I'll get. Now this is a constant term, right? So I'll just write it as constant. Now, what is k? We have seen k to be equal to log n base 4 by 3. So let's replace that here. Let's replace that here. When I replace that, what do I get? I get n into 13 by 12 power log n base 4 by 3 minus 1 by c. This c is basically this constant, 1 by 12. Because anyway, for asymptotic analysis, these constants don't matter too much, right? So now what happens here? Now, if you look at this, there is this nice formula that we have also discussed in the course, right? In some sample problems, we said that this is same as this, and you can simply prove it by taking log on both sides. If you take log on both sides, this becomes log c multiplied by log a, right? If you take log with base b on both sides, right, this becomes log c base b multiplied by log a base b. Similarly, if you take log base b on this side, you'll get log b base a into log b base c, right? So if you take log on both sides, you can prove this equation. From this equation, if I apply it to this, if I apply it to this with this being equal to a, this being equal to b, and this being equal to c, right? So I can write this as n power log 13 by 12 base 4 by 3, right? And now if I compute this using the scientific calculator that you have, right? So this will become n into, so this will become n power 0.27. So this will become n power 0.27, right? So this will become n power 0.27. So this whole thing becomes n power 1.27. This multiplied by this becomes n power 1.27, right? So what is the option that was given to us? The option that was given to us is Tn is order of n power 3 by 2. What is 3 by 2? 3 by 2 is nothing but 1 by 1.5 when k equals to 3. When I solve it using recurrence relation, what do I get? I get order of n power 1.27. Of course, 1.27 will be big O of n power 1.5 because 1.5 is greater than 1.27 and 1.5 is nothing but 3 by 2, right? So if I solve it using recurrence relations, this statement is true, right? This statement is true. Of course, it will take you considerable, non-trivial amount of time to solve it, to go through all of these steps, even with practice. Like this took me like 4 or 5 minutes, even with practice, to solve it. Okay, because there's so many places that you can mess it up and go and make trivial errors. Okay, so that's option 1 is true. What about option B? Option B says Tn is order of n log n if k equals to 3, right? So we already know when k equals to 3, what did we get? N power 1.27. So we have to prove that n power 1.27 is order of n log n. Okay, now let's compare n power 1.27 with n log n. Okay, let's compare both of them. So I can write n power 1.27 as n power 1 multiplied by n power 0.27, and I'll compare this with n into log n. So let's cancel n's here. Here I have n power some constant. Here I have log n, right? Obviously n power some constant. If you remember the order of functions, right? This is n power constant c, where c lies between 0 and 1, right? This grows faster than log n. So this is not order of log n. So this statement is false, right? So option B is false. Now let's go to option C, right? Option C says Tn equals to order of n log n if n equals to 4. Okay, so let's actually place n equals to 4. When k equals to 4, I'm sorry. This should be k equals to 4. I'm sorry, not n equals to 4. Here also k equals to 5. Sorry, I think that's here k equals to 3. Yes, it should be k equals to 4. I'm sorry. So when k equals to 4, what happens? T n by k, right? So this becomes T n by 4 plus T 3n by 4 plus some constant. So if you notice, this is very much like quicksort, right? What happens in quicksort? In quicksort, if my array, if the pivot element that I have always breaks the array in such a way that I have n by 4 elements here and 3n by 4 elements here, right? If this is what I have in my quicksort, this is the time complexity of a quicksort. If your quicksort every time breaks your array in such a way that 1/4 of the elements are here and 3/4 of the elements are here. And we know from quicksort analysis that for something like this, the time complexity is order of n log n. So this is also true, right? Very straightforward. So this case is the easier case. Now let's say if when k equals to 5, what happens? Again, since you wanted us to do it using a recurrence tree method, let's solve it. Okay. So this is what your recurrence relation looks like. And again, n by 5, 3n by 4, n by 5 again, 1.5. See, very similar structures if you notice. This is very similar to what we have done when k was equal to 3. If you look at this whole thing, it will resemble a lot of what we have done when k equals to 3. Right? 1 by 5 into 1 by 5, 1 by 5 into 3 by 4. Okay, similarly, 3n by 4 will be 3 by 4 into 1 by 5 and 3 by 4 into 3 by 4. Now, if I sum up these two, because that is the time complexity to combine these solutions, right? It comes to 19n by 20. Now, if I keep doing it in the kth at depth k, right? At kth level here, I will have this tree. This path will be 1 by 5 power k into n, while this path will be 3 by 4 power k into n, and this path is going to be longer. Since this path is going to be longer, right? Since this, and the sum of all of them will be 19 by 20 power k minus 1 into n. Since this path is going to be longer, right? What will my k be? Because this path is the length of this path, let's call it k. The length of this path, let's call it k. What will k be? K will be log of n base 4 by 3. Right? Again, same story. This is just like the previous case. Right? So now again, so just like in the previous situation, I simply add n 19 by 20, 19 by 20 square, 19 by 20 cube, so on and so forth, 19 by 20 power k minus 1. Right? Again, I remove n out and this is what I get. Here, if you notice, this r, see, this is also a GP. If you think about it, this is also a GP. Right? If you remove n out, this is also a GP. But in this GP, your r is 19 by 20, which is less than 1. So the sum of GP will take this formula now. Okay, this is your sum of GP. This is the formula for sum of geometric progressions, right? So now if you have this as the sum of GP, right? Now let's go here. If this is your sum of GP, then what is the sum? You just replace this formula and you get this. Right? Now again, I'll apply the same trick that we discussed earlier to simplify this, because your k, remember what is k? K is log n base 4 by 3. Right? So I replace this k here using this formula. And again, this is the formula that we discussed a while earlier. I'll reuse this formula and this is what I get. Now, if I simplify it, here is where things get slightly tricky. When I simplify this, what do I get? I get n. Okay, when I simplify this, what do I get? I get n power minus 0.17. Right? So again, this 1 by 20 became my constant here. Right? Again, this part, when I simplify it, I get n power minus 0.17. So again, multiplication, this is what I got. Now, the question here is, the statement that it says is, Tn is order of n log n. Let's verify that if it's n log n, right? Which means I have to compare this. Now I have to compare this with n log n, right? So let's remove n outside. So this is what I have, and I can cancel out n's here. So this is one term I have, this versus log n, right? Now look at this. This term is always positive because n is positive. Because n is positive, this term is always positive. So 1 minus this term is always less than 1. Right? This whole term, because 1 minus this term, which is positive, so this is less than 1. While log n, for n greater than equal to 2, this is going to be greater than 1. Right? So this term is greater than 1 for all n greater than equal to 2. Greater than equal to 1. right? And this term is going to be strictly less than 1, which means this term is greater, right? So this term certainly is less than this, right? Very simple, right? So hence, this case is also false, right? Hence, this case also is false, right? I hope this is.
Question is false.
Sorry.
Question they're asking which option is false.
Yeah, yeah, yeah.
Option B we already mentioned it.
Option B is false. Okay, one second. So this is option D, right? So what happens here? This is less than, one second. I'll just clarify it here. So this is option D, right?
Option.
Okay. So
This is true.
one second. Let me see if this is true. One second. So this, one second. This is less than 1 always, and this is greater than 1, which means this is okay. Let me erase this. Let me write it step by step. So this is less than this. If this is less than this is going to be less than this, which means this is going to be less than this, which means this is going to be order of n log n. Sorry, this is big O notation, right? This is basically an upper bounding, right? Sorry, my bad. Yes, so this statement is true. So this statement is true. I'm sorry. Okay, because this, okay, I'll repeat it again. I also got confused a little and got carried away. Sorry. So this is always less than 1, right? And this is greater than equal to 1 for all n greater than equal to 2, which means this term is going to be less than this term. If this term is going to be less than this term, then this term is going to be less than this term, which means this is going to be less than this term, which means the total time complexity is less than this. What does it mean? It means this is an upper bound on this. If this is an upper bound on this, then obviously what you get here, right? Then obviously what you get here, because you're using big O notation here, you can say this term is order of n log n. Yes, this statement is true. I'm sorry, my bad. Got confused with the signs here. Okay, sounds good. Okay. So of course, this question takes a lot of time. You could have just, of course, once you find something, I think the question was which of these options was false. I've not written the question here clearly. That's why I got a little confused here. Okay. But this is how you solve with reconciliations, especially these complex reconciliations, if you want to solve it using recurrence trees. Okay. Thanks for the correction. Okay. So the second very popular question that was asked here was about Dijkstra's algorithm, right? So Dijkstra's algorithm, this is a very important thing. I think we gave this as one of the exercise problems or sample problems, right? So now this is actually a very interesting question from, I think, 2006 GATE, right? So in this case, what happens here is you have negative edges. Look at this. You have a negative edge here. You have a negative edge here. But still, even though you have negative edges, your Dijkstra's algorithm still works okay on this. So the condition here for Dijkstra's algorithm is Dijkstra's algorithm is not guaranteed to work. It may work. It may work when you have negative weighted edges, but it is not guaranteed to always work. That's the important part. It's not guaranteed to always work. Actually, we also researched a few research papers to see if there are specific conditions. Okay, we tried to find if there are specific conditions under which presence of negative edges will still make Dijkstra's algorithm work. But we could not find any solid research paper or any research work which says if these conditions are satisfied, right, then Dijkstra's algorithm with negative edges will still work. Okay, we couldn't find such a solid, concrete research paper or even article anywhere for that matter. Okay, so there might be instances where graphs contain negative weighted edges where Dijkstra might work, but it is not guaranteed to always work. For example, let's look at this simple case, right? I have vertices A, B, C. Suppose this is my source vertex, right? If I start the whole thing here, then what happens to Dijkstra's algorithm? Let's go step by step here, right? So if this is my source vertex, what happens now? Okay, so first I reach here. So this will be 6. Its predecessor will be A. It will be 1. Predecessor will be A. Now this is already removed from the priority queue. The next thing that I'll remove from the priority queue will be this, because this has a weight of 6. This has a distance of 6. This has a distance of 1. Now when I remove this from the priority queue, right? What does it mean? In Dijkstra's algorithm, when I remove something from the priority queue, that means I already have the shortest path here, right? So I remove this. There are no edges starting from here, so nothing to do. Next vertex that I'll remove is this. When I remove this, because I have a negative weighted edge here, right? Look at this. I have a negative weighted edge here. Now, which means there is actually a path, which means if I now relax this edge, if I relax this edge, this becomes 6 minus 4 minus 20, this becomes minus 14 comma b, right? But I've already removed this from the priority queue, right? I've already removed this from the priority queue. So when I have a negative edge, even with a very simple example like this, we can show that Dijkstra's algorithm fails miserably, even with a very simple example like this. Okay, this is a very simple example where Dijkstra's algorithm will not work, because Dijkstra's algorithm will conclude by saying that the shortest path from A to C is this path, while actually the shortest path, if we apply other algorithms which can accommodate negative weighted edges, the actual shortest path is this. Okay, with a length of minus 14, but Dijkstra will not be able to find it. Okay, this is one of the biggest limitations of Dijkstra. But when you have negative edges, it may work. It may work. We couldn't find the exact conditions under which Dijkstra's algorithm with negative edges is guaranteed to work. We know one case where it's not going to work, which is negative cycles. If you have a negative cycle, Dijkstra will surely fail, right? Dijkstra will surely fail, just like Bellman-Ford, right? So when you have a negative cycle, any single source shortest path algorithm will fail. That's guaranteed. Okay. But if you have negative weighted edges, there are no specific conditions that we could find where this might work. The only thing Dijkstra says is it's not guaranteed to work, but it may work, like this example that we have in the solved problems or exercise problems. Okay. This is important. So I hope this is clear. Again, if somebody finds some research paper which says Dijkstra's algorithm with negative edges with some conditions will always work, can you please forward it to us? I would love to read it, and we'll also cover it as an additional topic here. But I couldn't find a research paper. I actually Google search for it. The only option I can think of is ask a professor who is researching on these topics, and because they will certainly be far more knowledgeable on, because they'll be more up to date with research than somebody like me who has not worked on this area very extensively. Okay, we'll try and find out if there is some work on that front. Okay, so here is the next very interesting, confusing question. This is like super confusing question. Okay, so the question here is this. Again, there are multiple solutions. We debated for almost an hour for this problem, right? So consider a hash function that distributes keys uniformly, right? So it uniformly distributes keys. Just a second, folks. Just give me a sec. Okay, so now I think I'll be able to write. Yes. So it says it. Okay, sorry. It distributes keys uniformly. Okay, that's what it says. Very good. The hash table size is 20. After hashing of how many keys will the probability that any new key hashed collides with the existing one exceed 0.5? So we gave the answer as 10 because we said, imagine you have your hash table. Imagine you have your hash table with 20 elements, right? Imagine you have your hash table with 20 elements. If 10 of them are filled, right? Then when I insert the 11th element, what is the probability of having a hash collision? It will be 10 by 20 because 10 of them are filled, right? Because remember, the hash function distributes keys uniformly, and this is equal to 0.5. One of the problems with the solution is in the question it says exceed. It doesn't say equal to 0.5. It says exceeds 0.5. But here we are getting exactly equal to 0.5. Right? So if you take this English question very carefully, the answer should be actually 11 and not 10, right? Because it says exceeds 0.5, not greater than equal to 0.5. Okay, but if you notice, 11 is not an option that is there, right? Again, the problem here is this question's terminology is very confusing. And I think this is a question from GATE 2007. Unfortunately, the GATE Council hasn't released official answers for these. So we tried to search for official answers for GATE by the GATE Council for this. We couldn't find it because it says, what does it mean by the new key hashed? What does the new key here mean? Is it the key right after that or any key? So there is a lot of confusion in the terminology here. So an alternative interpretation here is, okay, an alternative interpretation that we discussed amongst the team is, because if the answer is 11, that's not there in the options, which means our interpretation may be incorrect. So I wanted to give you an alternative also. The alternative here says, because there is a lot of confusion in the question, unfortunately. I wish the people who set this question paper were much more careful when they wrote the questions, I hope. Anyway, so the probability that's asking here is probability of, so let's assume what it's asking is probability of at least having one collision in k hashes. This is an alternative way of interpreting this, right? Because it says after hashing of how many keys will the probability that any new key hash, again, this new is the term here. Again, we fought a lot in the team on whether this interpretation should be correct or the previous interpretation should be correct. But let's see both alternatives so that you understand, in case hopefully next time when somebody gives you a much more clearer question, let's assume what they're asking for. Let's assume, okay, you may disagree with this interpretation just like me. I disagree with this interpretation because I was not fully convinced, but I thought I'll cover this. Imagine they're asking for, just imagine for the sake of this discussion, that they're asking for probability of at least one collision in k hashes, right? And we want to find what this k is. So they want us to find the probability of at least one collision in k hashes to be greater than 0.5. Let's assume this is what they're asking. Now, how can I write this probability? I can write this probability as 1 minus probability of no collisions in k hashes, because the probability of at least having one collision plus the probability of having no collisions is equal to 1. Right? Because those two are completely opposite to each other, right? Or because only one of them can happen, right? So now, if this is the case, we have the 1 here. What is the probability of no collisions in k hashes? Okay, let's compute that. What is the probability of no collision with the first hash? When I start with the first hash, there is nothing else to collide with, right? So the probability is meaningless, right? It is certainly not going to have any collision with the first hash. But the moment I have the second key that I'm hashing, there is a 19/20 probability that it might hash to this. Imagine I have one key that is present here, right? I have 1 to 20, let's say, right? The second key, this is K2. Let's assume K1 is already here. When I try to hash K2, because K2 is equally likely to be hashed to any of these buckets or slots, the probability that K2 will not hit this and not collide is, because there are 19 other empty slots, it's 19/20. The probability that the third hash does not collide with anything is 18/20. The probability that the fourth hash does not collide is 17/20. So on and so forth. The probability that the kth hash will not collide is 20 minus k plus 1/20, where k is less than 20. K is less than equal to 20. Right? Otherwise, this probability is meaningless, right? This becomes value greater than 1, right? So this is only valid while k is less than equal to 20, right? So yeah, it will work even if k equals to 20. Yes. Yeah. So it will work even here. I think it will work even with k equals to 21. The probability will become 0. Probability will become 1. Yeah, this will work even if k equals to 21, because 20 minus 21 plus 1, this will become 0. Right? Anyway, we don't care about it. So this probability now should be greater than 0.5. Right? Now, if you replace each of these values, 5, 6, 7, 10, this will work out when k equals to 6. If you just take k equals to 6 and solve this manually, you'll get that this value, 1 minus this value, is greater than 0.5. So the right answer could be interpreted as B, if this is the interpretation. Right? Again, to be very frank with you, this question, whoever said this question, they really messed it up, unfortunately, creating tons of confusion. Okay. But imagine if a question like this was asked in the future, with very clear terminology, that this is what we are looking for. We want to show you how to solve a problem like this, because we have not covered this type of example earlier. Okay, sounds good. So some students have asked for a couple of other topics like expectations in probability. There is one problem where I didn't use expectations, but I solved it using some simple probability. There is also the birthday paradox problem. So I think there is no point in discussing right now, because to explain expectations, I have to explain what a random variable is, right? And there is a lot of mathematics that I need to go over it. Even for birthday paradox, it is better we do it as part of combinatorics, right? And trust me, if I forget it, do remind me. I'm sure I'll not forget it, because we have written already notes for all of these topics. So I'm sure we'll go back to expectation. We'll come back to these problems and you'll have a much better appreciation and ability to solve these problems once we finish discrete maths, right? Once we learn discrete maths, because there are a lot of these interlinks, right, in computer science. Some of these problems require knowledge of more than one subject. So you'll be able to do it eventually, but let's be slightly patient and wait for discrete maths. Okay, sounds good. So there is another point which some of your students have mentioned, the relationship between BFS, prims, and Dijkstra's, right? If you think about it very simply, BFS uses a queue, right? BFS uses a simple queue, while prims is using a priority queue, and it's using the cut property every time. What is it doing? In prims algorithm, I have a set of vertices that are already removed from my priority queue, and I have a set of vertices that belong to my priority queue, right? Now what do? I try to add the edge. I try to add an edge from any of these vertices to any of these vertices that has the lowest weight. That this is the core idea. I think we have explained this when we learned Prim's algorithm also. This is the core idea, because Prim's algorithm internally is using the cut property. Okay, somebody asked, what is the use of cut property? Again, there are tons of problems, practice problems, and also solved problems where we've used cut property to compute minimum spanning tree very, very quickly. Right? You can compute minimum spanning tree very, very quickly using, if you have to do it with pen and paper in an examination setting, cut property is super useful. Okay. So just see some of those examples, you'll be able to better appreciate them. But in Prim's algorithm, there is no concept of relaxation. See, relaxing an edge is very different from what we do in Prim's algorithm. When I relax an edge, let's assume I have a vertex u and I have a vertex v. Let's assume I have u dot d, and this is some weight, right? So let's call it w, and this is v dot d. In relaxing an edge, I'm going to sum up these two and compare it with v dot d, right? And relaxing an edge is what I do in Dijkstra's algorithm and other shortest path algorithms, right? Again, in both Prim's algorithm and Dijkstra's algorithm, I'm going to use a priority queue. But in Dijkstra's algorithm, I'm going to use a relaxation method where I'm going to take this distance plus the weight and compare it with v dot d, right? So I want v dot d, right? If it is greater than u dot d plus w, then I update it. This is how I relax and update the predecessors and update v dot d, right? This is what happens in the relax. But what I'm doing in prims is not relaxation. Remember what I'm doing, because you're not summing these two things up in prims algorithm. You're not relaxing. This is very, very important. You're only using the cut property, right? So there's a lot of confusion for some students on why isn't prims and Dijkstra's the same? They're different because in the case of Dijkstra's algorithm, I'm taking these two sums and comparing. Right? In the case of cut property, what am I doing? If I have a vertex u here, vertex v here, right? I don't care what u dot d is, right? I only care about this edge length now, right? I only care about this edge length, right? And if this is the smallest edge between all the vertices that are not part of Q and that are part of Q, I will simply add it to my minimum spanning tree. Okay, I hope this is clear. The next thing that I wanted to cover was just a couple of general things. This is very important for us. We have students at all levels, trust me. Okay, so that's why right now we are planning to give, and some of the students were panicking because we have started giving harder problems, as some students have requested for harder problems. But we are thinking that we need to help every student at every level. There are some students who are preparing for GATE the second time. There are some students who are doing it the very first time. And we have to prioritize everybody. That's our core responsibility, right? So we thought when we give practice problems, we will give at least 60 practice problems that are medium or easy, so that people don't get discouraged and give up. But of course, we will give you 20 to 30% problems which are slightly harder. By medium, I mean at GATE level. Okay, by medium, I mean GATE level. Okay, 20 to 30, maybe 40% will give you hard problems, which are slightly harder than GATE, not too much harder than GATE, slightly greater than GATE. I don't want to give you problems which are super hard than GATE. That doesn't add any value to your preparation, unfortunately. But there are certainly students. I also understand that there are students who are at a very high level, in the sense that they are already prepared. They know most of these topics, and probably this is the second time they're preparing, or they're very quick with preparation. See, we have to be honest that students are at various levels. Okay. And of course, if you put in the effort, whichever level you are in, you should be able to make it. But we want to encourage you in this journey and not discourage you or demotivate you. So if you are one of the students who is really brilliant or who's doing it the second time. There are some students who are doing it the third time also. My suggestion is pick up a book like CLRS, solve the exercise problems, right? Because we want to keep this constraint that 60% of problems will be at medium level. Maybe 10% will be easy level also. Probably this will be at 60 to 70, to be honest with you. This will be 60 to 70. About 30% of questions will give you at a hard level also. So that some of the students who are doing this for the first time are not discouraged. Okay. So for those of you who think some of these problems are too easy for you, of course, please be my guest. Solve CLRS problems. And if you Google search for CLRS problems, there are tons of solutions available and multiple solutions available online. And if you're stuck anywhere, please do reach out to us. We'll try to find the best solution and explain it to you, right? So my suggestion for data structures and algorithms, if there is one book that you want to practice from for harder problems, just go to CLRS. For every topic, go to exercise problems. For example, let's assume we are doing min heap, right? Go to the min heap chapter or the heap chapter, right? There is a heap data structure chapter. Go there. Try to solve as many problems as you can. And if you solve CLRS, I mean, that's like superb. That's like more than sufficient preparation for GATE. Trust me. Okay. So just wanted to make this announcement so that some of the students who are doing it for the first time are not discouraged completely. Please try to understand that. Okay. Sounds good. So
Small announcement. So DX will have a subject-wise test.
oh yes, I've already done that announcement, but anyway, I'll make that. I'll just change the screen. We'll do that. Yeah, we'll have that for sure. Just let me just stop screen sharing and yeah. So yeah, what Subara was mentioning right now was, as I just told you a while ago, as soon as data structures algorithms is completed, we have 3 more topics. We should finish them in 3 to 4 days at most. We'll try to finish them. Today is 23rd, right? By 28th, I think we should be done. And there are not too many topics there. There is dynamic programming, there is greedy algorithms, and complexity classes. Again, we will revisit complexity classes in theory of computation also. So don't worry about it. We'll cover some of the basics here. So once we finish all of them, let's have subject tests and also take 2-3 days maybe to prepare, revise everything, get all of it. Any questions you have, please shoot them in the comment section. Okay. So once you finish this, as somebody asked, more practice problems, we'll give you a ton more of practice problems. Please don't worry about it. And we want you to practice more, because practice is the best way that you will remember, revise, and be prepared actually. So we understand that you need subject-wise preparation also. We are already preparing those tests, and we'll have them as soon as the rest of the content, rest of the three topics are finished. We'll get going with those, and hopefully by next week we should pack this up as we thought. By the last week of March, we wanted to pack up this whole thing. We'll pack it up and we'll practice a few full-length session tests. For these tests, my suggestion is this: please try to sit in one go and solve them. Okay, if you can find that time, right? Because it's okay even if you do one question in the morning, one question in the afternoon, etc. But it will be great if you could say, okay, this is 1 hour or 2 hours I'll sit. I want to solve the whole test. That way you're also practicing for speed. Remember, GATE is not just about conceptual knowledge, it's also about speed, right? If there are 2 people with almost similar knowledge, if one person can solve problems faster, he will have an edge, right? And especially if the question paper is easy, the difference between the first ranker and the 100th ranker and the 500th ranker will just be a couple of questions, or maybe at most a handful of questions, right? So speed is certainly important. Please. So when you practice, it's also good. I'm not saying it's critical right now, but if you get started from now, that mindset will sink in. That mindset is important, because that way you learn to solve questions faster. You'll try to find or leverage properties or use properties like cut property for MSTs, right? You learn to use these very quickly and solve problems faster. You'll be able to think of boundary cases faster. And that only comes with practice. Okay. If you ask me today for some of these problems, I take too much time. And some of our teammates actually solve much faster than me. And that's because they've been thinking of new questions. They've been solving questions much more than I do. And they're thinking very creatively about how to solve a question fast, right? While I am trying to solve a question rigorously, right? So it's very, very important that we practice speed also. And don't worry, we'll give you tons of practice once the 3 topics are over. And that'll also be like your revision. Okay, it will be a combination of revision and practice. So we'll do everything from the insertion sort, asymptotic analysis, to complexity classes, everything in between. That way it's also a great way for you to test assimilation of information and revise stuff that you have learned maybe 2 weeks back or 3 weeks back. Okay, that's also very important. It's very easy to forget in gate preparation, trust me. It's very easy to forget it. So it's very important to practice more so that you don't forget some of these concepts. Okay, folks. Yeah, I don't want to waste any more of your time because it's a Saturday evening. I know some of you may plan some time out in the evenings or early in the morning. So see you soon, and all the best, and have a good weekend. Spend time with family and friends. Hang out with your buddies, and yeah, be safe. Have a good time. See you again on Wednesday. Hopefully by Wednesday we should have most of the other topics, and we'll plan accordingly. But please finish off these 25 problems by Monday morning. Please try to do that. Monday morning is day after tomorrow, right? So you have like 36 more hours. Please try and finish, assimilate everything in the graphs, solve all the problems. We also uploaded all the solutions. Please verify them. Any questions you have, please shoot them in the comment section. We'll try and resolve them ASAP. See you folks. Thank you. Bye bye.